Good evening, everyone. I'm Anish Ambekar, PMRF and PhD candidate from Aerospace Engineering ISC Bengaluru. Welcome to this week's live interaction for the session for the NPTEL course, Dynamic Behavior of Materials. In today's session, we'll be covering the course content allocated to week 12. Specifically, it contains a brief on deformation twinning under shockwaves before moving on to details about shear bands as well as dynamic fracture. So what is deformation twinning under shockwaves? So, as we have already looked in, I think the week 8 content, mechanical twinning can occur in certain scenarios. One of those is shockwave loading. So, let's write it down. Deformation twinning, and it seems to be favored under shockwave loading. Shockwave I write in short as SHW loading, and is even observed for metals that do not exhibit these uh, these twins by conventional loading at ambient temperature. So this depends on pressure. So a certain threshold needs to be crossed by the shock wave. So an example of the same is for nickel, the threshold is around 35 GPa. Another factor is crystallographic orientation. In deformation twinning, you have in mechanical twinning, you have the like a reflection symmetry being coming up. So an entire layer may be missing in the arrangement, in the atomic arrangement. So that you can think it depends on the applied resolved shear stress. So it requires tau RSS to exceed a critical value for a given deformation for a given twinning plane as well as twinning direction. The third factor is stacking fault energy. So as the stacking fault energy decreases, twinning increases. Another is the pulse duration. There is a threshold duration exists for twinning, and beyond this threshold, twin density increases up to a certain value, up to a certain maximum value. So it basically increases and then saturates. Another affecting factor is the existing substructure. So, dislocation, as we know, dislocations and twins are competing mechanisms. So dislocations and twins are competing mechanism, meaning if dislocation density rho is high, twinning is low. And another important point to note that twinning under shock wave, same as twinning by conventional waveform. So fundamentally, there is no change like microstructurally between the two applied between what kind of loading has been applied, whether it's a shock wave or it's a conventional. Okay, so the next part uh, is related to shear bands. So shear bands are a type of instability, adiabatic instability. So right, shear bands, SP in short. So these are regions with highly concentrated plastic deformation, and they act as precursor to failure. Important thing to note is that it can be used in certain some applications, both civilian and military. An example of the same is rolling. So suppose you have a specimen being rolled, right? So the specimen, when it goes to the roller, it's flattening out a bit, and you can see these shear bands are formed, and they are basically regions of decreased strength. There are a high amount of internal flaws. So rationale for shear bands. This was given by Zener and Holloman all the way back in 1943. So it goes as follows: when a material undergoes an element of strain T epsilon adiabatically, then the stress is raised by work hardening and lowered by uh, associated temperature rise. As such, shear bands are formed if thermal softening overcomes work hardly. So two competing mechanisms here. Uh, as if the deformation rate is low, when the material will undergo some amount of strain, right? It will the stress will be raised due to work hardening. If for whatever reason the deformation rate is high, then what you will see is instead of the deformation process being isothermal, which is like if there is any heat being generated in the process that spreads out and the material comes back to ambient temperature, you will have the process slowly shifting to an adiabatic, uh, from isothermal process to an adiabatic process, thermodynamically speaking, strictly depending on the rate of the applied rate of deformation. What that does is you have what that does is you have to these things these two things uh, this adiabatic process would result in increase in temperature in the localized region, which is basically thermal softening of the material. So you have two competing mechanisms, one trying to increase stress due to work hardening and other trying to decrease stress due to thermal softening. So you can theoretically understand that if the deformation rate is sufficiently high so that the process becomes so that the process can be considered adiabatic and the temperature rise associated with it is sufficiently large, that would mean that at some point your thermal softening would overcome your can overcome your work hardening. Again, depending on the material properties, but that thing can happen. That is the spot where we are. That is the critical spot we are interested in looking at when looking at these shear bands. So shear band formation, what helps, what doesn't help. So it's favored by thermal softening and geometric softening. This refers to like usually some sort of internal microstructure rearrangement, and it is in turn opposed by strain hardening as well as strain rate hardening. If one were to understand in a schematic manner, one could draw uh, as follows. Suppose you have a shear stress tau applied, gamma is less than some critical value of shear rate, so that would result in homogeneous shear throughout the body. Next, you have if it increases in if the value of shear stress increases till a critical value, then you have tau tau gamma greater than gamma critical, then you have a shear band formation. This is usually very thin, of the order of microns. So shear band formation. And one way to think about this is if one were to draw how strain localization looks like. We are simply plotting how shear strain uh, looks like for different strain values. So you have a homogeneous shear strain, homogeneous shear at gamma naught, gamma 1, at gamma 2. And then at some critical value, you see this gamma critical, and then beyond that, gamma 3. So strain localization is seen for beyond a particular critical value, and that critical value in turn can be evaluated by looking at your shear stress shear strain curve. So if I plot tau versus gamma, it reaches a critical value. This is the adiabatic shear stress strain curve, beyond which it can no longer support increases in stress. So as an instability is formed at that maximum, the plot. So the strain inside shear band can be very high. For example, steel, which is 10 to the power 3 second per second shear strain rate, and for this gamma critical equals 0.4, and gamma in the shear band can be as high as say 40, whereas steel specimen, this is local shear, whereas steel will fail for gamma of the order of point gamma around zero point 0.5. So you could have a much higher shear strain value. That is what we see inside the shear band. The shear band is very thin. You could look inside the reference book, Mark Mayer's book, wherein you have some micrographs which help us understand how the shear bands look like. And how they play a role in failure can be better understood by this. Suppose this is my shear band. You can see that locally the shear strain is higher inside the shear band. And then again globally it has the same shear strain. So you could have something like this. You have a void formation and later coalescence inside the shear band. And your void diameter, we can think of it as approximately equal to the shear band thickness. And why the voids? These voids are produced by tension. Specifically, the flow stress inside, because the material has weakened significantly, the flow stress inside the shear band is much smaller than its surrounding, which in turn leads us to void formation becomes easier. Another, okay, so with this in mind, we'll move ahead with a constitutive model. Again, this is based on the same uh, rationale given by Zener and Holloman. So we can write shear strain as a function of temperature. Shear stress is a function of temperature, shear strain, and shear strain rate. If one were to take the first derivative change, you have partial derivative of tau with respect to temperature at constant shear strain and strain rate, dt plus partial derivative of tau with respect to gamma at constant t comma gamma dot. T gamma plus partial derivative of tau with respect to gamma dot at constant temperature, comma strain rate d gamma dot. Right. So this is how the equation looks like. And if we assume adiabatic shear band instability, in this case you have dou tau by dou gamma, d tau by d gamma equals 0. And this comes from this plot, so like this critical region. And again, if we assume for constant strain rate condition, you have, so this is how typically the experiment would be performed. You have d gamma dot equal to 0. Therefore, we have d tau by d gamma equals dou tau by dou t into dt by d gamma. This is how the equation looks like, and not then, just yet. So if we are interested in finding the increase in temperature, to find the increase in temperature, we have uh, increase in deformation energy. dW is equal to tau d gamma, and increase in temperature as rho Cv dt is equal to beta times dW. This is usually zero point 0.9, which is, so like 90% of the plastic work converts to it. So you can write delta T is equal to beta by rho Cv integral tau d gamma. We usually can write thermal softening as shear stress at a given temperature is shear stress at a reference temperature T naught. So melting temperature minus applied temperature upon melting temperature minus reference temperature. And using a power law dependence between stress and strain, you have basically tau is equal to A plus B gamma raised to n, the power law, and then multiplied by the thermal softening, which gives us d tau is equal to minus A plus beta gamma raised to n upon Tm minus T naught partial derivative of, as partial derivative of temperature, assuming constant gamma. So from this you can determine d tau by d gamma is equal to dou tau by dou t into dt by d gamma. Dou tau by dou t is basically this expression. So you have minus of a plus b gamma raised to n upon tm minus t naught into d tau by d gamma comes from here. dt by d gamma comes from there. So you have beta by rho cv a plus b times gamma raised to n. So using this, you can evaluate what how the this expression needs to be set to 0 to basically understand what the critical gamma value is. So you can do that on your own. Another important point is the metallurgical aspects. So You have homogeneous deformation at high shear strain for annealed copper and annealed aluminum, whereas shear band is seen for like brass 2024 T for aluminum alloy or 1040 steel, right? Shear bands can be classified based on optical observation as either deformed or transformed. The key difference is that for the transformed shear band, microstructure of the shear band appears very different. And suppose you have ASI and it is steel. Here we see a alpha which is BCC to gamma which is FCC transformation at 723 degrees Celsius. So if this comes from the unary phase diagram, we have already seen that. So if the deformation is such that shear band temperature T exceeds 723 degrees Celsius, you see gamma FCC grains inside shear band. And what you can do then is you can quench the whole apparatus to quickly cool, basically quickly cool it down, and then retain some gamma grains inside your uh, material. The grains in the shear band, these are very small, the diameter of the order of zero point 0.1 micron, and there is very low dislocation density. Usually in this grain, so like they'll be formed very small diameter, not a lot of dislocation. So like pretty much small grains spread throughout, right? One more thing is how the steps, associated steps inside this is, suppose you have a material that looks like this and which is being deformed. So you have these three grains, one, two, three, being deformed. This is the step one. So there is a uniform deformation applied, even if they have different orientation. In the second step, if the if the rate is sufficiently high, then if T greater or equal to Tm, recrystallization occurs. So you can see small grains coming up. Step 3 would be like in the same three grains. 2, 3. We have small regions coming up. So there is a new grain nucleation as critical deformation is reached, and the diameter of the new grain roughly varies as 1 over gamma square root of gamma dot. Then these grains increase. So I should plot it like this. These grains in turn increase with size, increase in size with deformation, and they in turn can also give birth to other children grains within. One final point regarding shear bands. So the hardness of material within shear band varies as per the material. So we have already seen that there are, from an optical observation perspective, we can classify shear bands as deformed or transformed. In the case of transform, because you would have a new microstructure coming up, you can easily expect that to have a different sort of hardness value. So suppose you have AISI 4340 steel, then you have changes in microstructure inside the shear band, and this is due to transformed shear bands. Whereas suppose you have something like titanium 6, 4 vanadium alloy, no change in hardness because it's a deformed shear band. Uh, an important thing is how these concepts all come together and connect, because that gives us a good idea into how we may use this physical uh, properties to our advantage. The next section that concerned was concerned in this course was regarding dynamic fracture. Before going into dynamic fracture, let us look at what fracture is. So fracture can be classified roughly into two types, brittle and ductile. And brittle fracture can be again classified as transgranular or intragranular. So what do we mean by that? Transgranular is, suppose the crack propagates through the grains. So this is the crack that is going through inside the grains. So there is a cleavage. It's also called as a cleavage crack. And the thing is that crack has a definite crystallographic orientation. Another one is the intragranular crack, which looks as follows. So in case of intragranular crack, you have crack moves along the grain boundary. And for ductile material, you can have transgranular crack. Because we have seen that in ductile materials, there will be dislocations and other type of defects, voids and so on. You basically have a void coalescence occurring. So something like this. You have a voids coalescent, right? So, in case of ductile materials, crack propagation requires more energy as plastic deformation needs to be overcome. One more important thing is that you see a crack tip blunting as the voids coalesce together, and you also see void coalescence leading to crack growth. So basically, these voids will join along the crack tip to which macroscopically would look like the crack is extending forward. So when we view this through a micrograph, so micrograph schematic, not exact, just have a look at this. In case of a ductile material such as aluminum alloy, you have a many microvoids, leads to ductile fracture. Whereas for a brittle material, so such as pure iron, you have many micro cracks, which leads to brittle fracture. An important concept associated with is the crack tip stress, and stress intensity factor. Not stress intensity, sorry, fracture toughness. So suppose we are trying to open up a crack, which is a mode 1 fracture. So it's the crack. It's an elliptical crack with semi-major axis as A and semi-minor axis as B. Suppose this is my origin and this is X and Y. I can plot how stress looks like. So this will be sigma 1 1 and this will be sigma 2 2. So the stress at crack tip is much larger than stress in applied material, and specifically the crack face opening stress. In this case, it's a sigma 2 2, so we are applying the load vertically, and the elliptical hole crack is being represented by an elliptical hole which is opening up. So you have sigma 2 2 which rises sharply. You use the stress intensity factor psi f to characterize the crack. And for mode 1, it's basically written as sigma root pi a. for mode 1. And when K1 greater or equal to Ki is critical equal to sigma critical root pi a, crack propagation occurs. And this KIC is basically a material property. For metals, KIC is of the order of 20 to 150 MPa root meter, whereas for ceramics, K1C critical is of the order of 2 to 5, this one, 2 to 5 MPa root meter. Right, there are other modes of fracture. So this that we have drawn here is basically mode 1. Mode 2 is you have, and third is this face is being pulled outside of the plane and this face is being pushed into the plane. So you have three fracture modes, 1, 2, and 3 respectively. For ceramics, we can see that the fracture toughness seems low. So there are some way to toughen a ceramic. In short, they are as follows. Suppose again mode 1 we'll be looking at it. The first way is fiber strengthening. Here we add ductile fibers which act as crack arresters. Energy required to extra energy rather required to detach fiber from ceramic matrix. Another one is something called as transformation strengthening. So an example of the same is suppose you have aluminum oxide matrix and inside you have zirconia grains. So here away from the crack you can have tetragonal zirconia grain, whereas near the crack you have monoclinic zirconia grain. So again some energy expended in the transformation. Third way is using microcracking. Microcracks. Third way is microcracking. Again, energy expenditure. So the way to toughen say, ceramics in this case, but in general, is that you want some amount of energy to be expended somewhere else rather than in fracturing the material. That's the easiest way to tackle this problem. So another important point is apart from plane strain fracture toughness, which is the K1's Ki critical that we are seeing. We have other parameters. So one of those is the energy release rate. Suppose this is the crack. We are applying a load P to open up the face that leads to a small displacement V by 2, right? So each face moves by V by 2 at load P. Therefore, external work done is F is equal to P into V, which leads to increase in strain energy, internal strain energy, which is U, plus crack growth. So energy required for crack growth, which is W. Condition for stable crack growth, this is A. Condition for stable growth, crack growth, d by dA of U plus W minus F equal to 0, which gives us d by dA of F minus U is equal to dW by dA. This dW by dA is nothing but R, which is the crack resistance, whereas d by dA of F minus U is nothing but energy release rate. So rate sounds like per unit time, but here it is per unit length of the crack. And we have the expression G is equal to 1 minus nu square to K1 square by E, which is nothing but 1 minus nu square K, sigma square pi A by E. The next factor is regarding energy release. Regarding the resistance, so G comma R can be plotted on the y-axis, crack length can be plotted on the x-axis. So you can see that G increases is proportional to A from this expression, which gives us, whereas the resistance to crack growth, A1 is the crack length, this is the resistance R. When G equal to GIC, crack starts to grow. And since the resistance R is constant, implies the energy release rate G will exceed R for any crack length A greater than A1 provided, which means crack keeps on growing. Again, from the expression, it should be pretty straightforward. So, lot of this is based on linear elastic fracture mechanics, which is for brittle materials. To get really deep into it, a course, a suitable postgraduate course for fracture mechanics can be looked at, or you could look at references such as Anderson. So, an important point is, see, when plasticity is high or considerable, which is the case for ductile materials, J integral can be used. And for linear elastic fracture mechanics for brittle materials, J equals energy release rate G. Pertaining to dynamic fracture, there are certain uh, unique conditions, so unique features. The first one is limiting velocity of crack growth. So this typically equals the Rayleigh velocity, and we'll understand why from the schematic. Suppose this is my material with a crack loaded with P. So the energy can go along the surface. This is path 2, and energy can go directly to the crack tip, which is path 1. Energy needed at crack tip for growth, which tells us that it is provided by external work P. So two pathways can be thought of. Path 1, bulk longitudinal wave and bulk shear wave, small fraction of energy. We've already seen this in, I think, week 2 lecture, how for an isotropic solid, for an isotropic like half plane problem where you have an impact loading, how the energy distribution looks like. So I think in that case about 74% of your energy goes to Rayleigh wave, which is basically your part 2. That was for an infinite solid. For a for this kind of problem, the energy distributions can change around. So for part 2, energy will travel using Rayleigh wave. This comprises of the most of energy. Second thing is crack branching, and this is done to decrease overall energy of system. So suppose you have a crack that grows like this, and then it splits into two, which in turn again splits into two, and so on and so forth. So this helps to decrease the total energy of the system. So how do we get at those? First, we'll look at the limiting crack speed. Suppose you have an elliptical crack, which is 2 AC, and this is my x-axis. This is my y-axis. Suppose I have, this is the expanded crack dotted in a dashed line. At this point, I'm interested in u velocity, v velocity. This is r comma theta. So the crack propagates with velocity du by dt is equal to u dot with an initial length AC and crack length at time t becomes A. So, right. So in this case, if we look at how the energy plot looks like versus crack length. Again, we know it's a straight line for G. For resistance R, we have GIC equals R. This is AC, and suppose this is the line A. Then this is the extra energy that you have. So you have got an excess energy which is given as ER is equal to integral AC to A G minus R dA, and with R as constant, you can juggle things around and then get how the energy release rate, excess energy changes with time. So one more plot that we have is A dot by elastic bulk wave velocity. This is 0, 0.1, 0.2, 0.3, 0.4, and this is 0.47. Somewhere here you have a limiting velocity. Oh, I forgot to put this is 1, 3, 5. This is A by AC. So you have got crack wave velocity as 0.38 C 1 minus AC by A. And this is evaluated for a brittle material with assuming Poisson ratio is 0.3 for an elastoplastic material, your behavior becomes much more complex. And the important takeaway here is that as your uh, crack, assuming your crack resistance remains constant, R remains constant as the crack length increases, you have a excess amount of energy being poured into system that leads to an uh, increase in stored energy that in turn would lead you to uh, expansion of crack, which basically has a limiting velocity, and that limiting velocity can be plotted as a function of the crack wave propagation. The crack propagation velocity can be normalized against the bulk elastic wave velocity, and we see that it has a limit, and that looks like this below graph. For crack branching cases, the rationale goes as follows. Suppose I am plotting G versus delta A now. This is my critical, minus A critical, 0 critical, 2A critical, and so on. Right, so at delta A equal to 0, I'll have some resistance value R. At delta equal to this, I'll have another resistance value 2R. When crack becomes 3 times as longer, I'll have resistance value as 3R. So here the crack length is AC, here it is 2AC, and here it is 3AC. What happens is that at delta A is equal to AC, sufficient energy exists in the system to drive two cracks, which means kinetic energy of the first crack, this is basically the parent crack, provides energy for the two cracks, which are the children cracks. As a result, the children cracks are slower than parent. What this also allows this crack branching phenomena is that the excess energy stored in the system decreases, making this whole situation more stable. Finally, we are interested in understanding what happens if. So this is similar to elastic wave propagation that we have seen, but suppose you have a stress wave approaching a crack. What happens is as it interacts with the crack tips start radiating. So the crack tips start radiating, and you have a and that looks like this. So there is some amount of crack free, not loaded, and after a while, I have to draw this smaller. So it's smaller, it's not to scale, but you have basically different wavefronts coming up. So this is a longitudinal wavefront, this is a shear wavefront, right? So stuff like this happens, and what basically means is you have the crack tip start radiating. And if one were to plot how the dynamic fracture toughness looks like, so KID by KI static. So this is one unity. This is time. Near the crack tip, you have a behavior that goes like this, and then after a while settles down. So what time here? So right near the crack tip, you can have your dynamic SIF increase compared to your static case. So apart from this, there is one more interesting application which is spalling. So again, that spalling happens because of release wave. So suppose you have a projectile hitting a target, and then a compression wave goes into the target, hits the free surface, returns back as a tensile wave. Similarly, uh, the compression wave that was generated inside of your uh, the compression wave that was generated inside of your projectile again hits its own free surface, returns back as tensile wave. Those two tensile waves will meet somewhere inside the target, assuming the target is much larger than the projectile, and that would essentially lead to a much higher, much increased tension. Those two waves would come together in this and lead to much higher tension values, which in turn would lead to fracture. So that's spalling. Again, they'll keep on reflecting across the boundary, and you can have multiple spalling happening for the same loading. So as the material breaks, some amount of energy from the tensile wave goes away inside the spalling. So after a time, you may have tensile waves coming up with multiple reflections, but you may see only some number of spalling incidents. So that covers roughly what we have for this week. Thank you for attending this lecture or watching it online. I think this is the last of the week, last week's content. We'll have one more extra session concerning applications. So we have chosen two or a couple of civilian applications, and we will be looking at them in a bit more detail. How we can apply all this knowledge into somewhere uh, that is industrially useful. Okay, so that's all from my end, and I'll see you again on the final session. Thank you.